Hello everyone, this is me Sadat from Arcanine Game Studios. Today we will be continuing with our ongoing tutorial series on terrain generation and we'll show you how to create this daylight system and this beautiful water shader. Now keep in mind, all of these shaders and tricks I am showing you up until now are meant to be cheap, which means they are not perfectly physically accurate and are meant to work on lower end devices as well. Now I will be tackling more compute intense shaders in later tutorials, but for now let us get the most from the least computation. Now as always, I will be linking the source codes in the description below, and if you find these tutorials helpful, please feel free to click like and subscribe, and don't forget to leave your feedback in the comments below. Also, if you know someone who might be looking for these kinds of tutorials, please feel free to share the videos. Now that the introductions are done, let us begin with the daylight system. The first thing we need for the daylight system are the sun and the sky. The sun will be a directional light node since we don't want the sun's brightness to fade in terms of distance, and the sky will be a world environment node. Now I've set the sky to be a child of sun, but it might make more sense to do it in the opposite order. However, like I said before, we're not trying to be physically accurate here, but rather just get the work done. Now if we move on to the code, it is a simple script which does some light color changes and rotates the sun around. Now as always, the script is a tool, which means it will run in the editor. It is a subclass of directional light, and following those are my exports. Now these variables can be tweaked from the editor, that's why I'm exporting them out. These are the duration of the day cycle in seconds, the colors for the different stages of daytime, and the base color of the sky. Now I've also added custom shaders to these values as well, but you can easily skip those except for the day cycle. I haven't really added an export variable for the sky node, and I assume it to be a default, but you can feel free to add a node path export to be able to choose different environment nodes. Now the first thing that runs in this script is the ready function. Let's look at it now. Once we're ready, we define the rotation speed to be 2 pi or 360 degrees divided by the day cycle duration. Then we reset the rotation values for the light and set the current light color to be dawn. This means we will always start from the break of dawn. We have divided the day cycle up in 4 quadrants, which are dawn, midday, evening, and night. We set the current time to 0 and set the sky color to be the base color of the sky. After this, we'll let the process function process and give the results. Okay, so in the process function, we rotate the light per tick, adjust the color of the light and the sky, and after this, we increment the daytime by delta and define the quadrant of the day based on the rotation of the light. Finally, we reset the tick if a whole day is completed. So let's look into the rotate light function now. It's a one-liner which just rotates the light in the x-axis based on the speed and delta. Notice it rotates in the negative direction as we are starting from dawn. Now look into the light color adjustment. It is a very simple function as well. Here we are just taking the absolute value of the sine of the degree of rotation of the sun and checking for the day quadrant. The sine value of the rotation will give us a value between -1 and 1, but since we're taking an absolute value, it will be within 0 and 1. If you know, sine of 0 is 0, sine of 90 is 1, and 180 is 0 again. Because of this, we can directly use the sine value as the mixed value for the linear interpolation of the sun's light color. For the first quadrant, we have the sine going from 0 to 1, and in the second, we have sine going from 1 to 0. In the third, it's 0 to 1 again, and then in the fourth, it's 1 to 0. That is why you will see that the color mix order is flipped in every quadrant. Now that the problem of the sun is solved, let's look at the sky. Now for the sky, we simply mix the base color with 45% influence from the sun's color and set the same color for the ambient light from the sky and for the distance fog if that is enabled. That's all it takes to create a daylight system. Hopefully this was useful for your next game dev projects, and now let's get to the fun part, which is creating the water shader. So for this shader, we start with the type spatial, then we move on to the uniform values. There are quite a few uniforms in this one. This is because I want to be able to change as much of it as possible from outside the code. We take in foam, specular, surface, and deep water colors. Then we take in the normal map for the water and the UV scale for the normal map. Next, we take the time factor for the waves and the visible depth of the water. This defines how clear or murky the water is. The next variables are the range of the foam and the amplitude of the vertex. Next, we have a varying value, which is the I vector. We need this to calculate the specularity. Now let's look at the vertex processor. We simply shift the vertices based on the normal map and amplify the shifts based on the amp value. Next, we calculate the world position of the camera or the looking angle by using the inverse camera matrix, which is the inverse transform of the camera, and we pass it along to the fragment. Now, if you know a bit about 4D matrices, it is an affine transform and basically holds the transformed value of the camera, which we need to invert. Now, we will be coming to the Fresnel function in a little bit, But for now, let's go to the fragment function. Now, in the fragment processor, we first read from the depth texture based on the screen coordinates. Then we need to unproject the depth texture and take its red value or the X value and convert that into orthographic projection. Now, for this step, I'm actually following exactly as it is from the Godot material source code. Now, after this step, what I'm doing is I'm multiplying the alpha with a little Z clipping offset. I have to do that to solve a little bug in Godot's GLES2 renderer, and I found this solution in the Godot GitHub discussion. Now let's get back to the shader. We apply the normal map and wrap it by the scale factor while shifting it by the factor of time to give the moving wave illusion. Up next, what we do is we define the depth of the normal map. Now in the next step, we find the depth fade between the depth coordinate of the world and the offset from the vertex Z value, and clamp it between the surface's alpha and deep water's alpha. Now this gives us the slight visibility underwater that we desire. Now the next step what we do is we take another alpha component, and this time it is for the foam mix. This is to show you the foam which happens on the edge of the water. Now for the next two values, this is where things get a bit interesting. These are the Fresnel values for air and water. N1 is the Fresnel value for air and N2 is of water. Now what this does is it gives us that nice shine on the water surface, as the Fresnel value gives you the reflectiveness of a surface. So what we're doing is we're calculating the Fresnel based on the Schlick approximation, which is a very fast way to approximate the refractive coefficient of materials. Every element has a refractive index, and this method allows us to simulate that in graphics applications without being a killer. Because the actual Fresnel math is extremely complicated and is not practical for real-time applications. So I'm not going to explain the equation, just know that there are plenty of mathematical references out there for understanding Fresnel, which I would definitely recommend you to study on, since it is a very useful function for all kinds of graphical applications. If you do understand that it gives you the bend of visual light between materials, which we need in every kind of transparent or translucent element. Okay, so let's get back to the fragment function and look at the next steps. So what we do is we calculate the reflectiveness based on the reflectiveness of air and water and the angle of viewing, which we calculated in the vertex shader from the eye level. And next we mix the shallow and deep water colors based on the alpha component. And then we mix the foam based on the foam alpha, and finally we mix that foam with the specular color based on the reflectiveness and control the shine based on the alpha of the specular color. Now, if you had followed my previous tutorial on the terrain shader, you'd know just how much I love to mix colors. And if you haven't seen that yet, I'll add a card to this video to link to that tutorial. Now the last step is to apply the alpha component to the alpha channel, and that is it for the shader. I hope you got a good feel for it, and if you liked it, please feel free to click like and subscribe, and I'll try to come back with more interesting tutorials for the next weeks. So stay tuned, and I'll see you on the next video tutorial. Thank you.